All right, so this isn't quite particle filters, but it's the key ideas that underlie particle filters. This is what we're going to talk about in this set of slides. And in particular, what's the trick for evaluating a multidimensional integral efficiently? How do you beat that curse where you don't have to write 54 loops that are all nested and just is bad? And that's what we're going to talk about today. This is the overview. And once again, I know I just said this, but let me just drive it home. If you're doing something like these optimal recursions, and particle filters are attempting to implement these recursions almost directly, but with a sort of very clever, tricky way of representing the posterior distribution. We'll represent this posterior as a set of so-called particles, these ideas. You've got a bunch of BBs, kind of, is one way of thinking about it. And how do we implement these recursions if we've just got sort of this cloud of points that we're tracking over time? And but theoretically, if we're thinking about the full distribution, we've got to evaluate this integral, and the amount of computation scales exponentially. And so although this is just a beautiful set of equations, and it's very concise, it's very compact, it's not practical, it's used a stronger word of impossible here in most cases, and this is a clever way of addressing that. There's a lot of discussion that's going to go into this, but I want to lay the framework and get some examples, and then we can talk about what's really happening, how to interpret it, hazards, and things like that. So, so this set of slides is generally about how to evaluate an integral, and I'm going to step aside from the state space framework for now and talk about just the simpler case of you want to evaluate an integral, and let's imagine this is a multidimensional integral, so x is a vector, and we're trying to integrate over all the values of x, some function g of x, with respect to x, and arrive at something that I'm going to call mu. Now, I've chosen mu to sort of echo your memory of mean. I've done that for a deliberate reason that I'll talk about in a minute. But for now, just imagine mu may not be the mean of anything. It's just what the value of this integral works out to be. And you'll see why mu was chosen in a bit. So this is hard to do, especially as the dimension grows. It's hard to do numerically. You simply run out of cycles if you're trying to do it numerically. And there's a group of techniques that have been used forever in statistics and in lots of other disciplines called Monte Carlo methods. And it's, I got to tell a little bit of a story here. I, as a graduate student, was really interested in artificial neural networks. And when I studied them, it turns out that the way that you get these to work is you've got all these parameters and you don't know what they are. And you start off by initializing all these weights as being random. And that always drove me crazy. I thought, look, if I'm trying to build something, if I'm trying to estimate something, it doesn't make sense to me to have a random number generator in the process of trying to build that estimator. Why on earth would I build an estimator of anything and have a random number generator in there so that my estimate, in some respects, is going to depend on whatever random number generator came up with? It always seemed intuitively to me a bad approach, fundamentally misguided to have a random number generator informing your estimate or affecting your estimate. I mean, that means every time you do it, you're going to get a different answer because you're initializing with these random numbers. Why on earth would you do that? And the irony is that Monte Carlo methods are driven by random number generators, and they're used for doing great things and solving really difficult problems. And it turns out a random number generator can be very helpful when you've got these high-dimensional nonlinear problems. So there's a bit of an irony in my mind that years later, after I sort of gave up on neural networks as a viable approach to solving some hard problems, I'm circling back, and I've run back into random number generators driving the estimates again. But we'll talk more about that. So if we're going to use a Monte Carlo technique to estimate mu, then the first thing that we're going to do is factor g of x into a product of two different functions. One I'm denoting as f of x, one I'm denoting as p of x. The choice of p of x is deliberate. P of x is going to have the same properties as a PDF, and we'll think of it as a PDF. So I can do this for any function f of x. I mean, the simple choice is to choose a uniform distribution over whatever the full range of the integral is, in which case this just becomes a constant, and this becomes the inverse of that constant. So the product gets you back to g of x. So we're taking an arbitrary function that we're trying to integrate, and we're representing it as a product of some function f of x and some PDF p of x. And as soon as you do that factoring of g of x into a product of these two functions, it makes sense why mu is chosen. Because if you look at this integral now as the integral of f of x times p of x, then that is the same as taking the expected value of f of x for whatever that PDF happens to be, whatever we choose that PDF to be. So that's why mu was chosen, because now, although what our problem really was to evaluate an integral, there's an integral involved when you're calculating an expectation, and by expressing g of x as a product of these two, we can even think of mu as the expected value of this function that came out of this factoring that we did. You guys with me? So, again, p of x is a probability density function, which means it's got to be non-negative over all values, and the area, the integral of p of x, has to be equal to 1. And we'll actually drop that constraint later if we have time. So here's the key idea, and this is really the key idea underlying particle filters as well. The key idea is that I can approximate an expectation as an average. When it comes down to it, I think that's what particle filters are essentially about. I can approximate an expectation as an average. We know that mu, where we're really trying to evaluate an integral, can be written as the expected value of f of x. And if I can generate a large sample, say n much greater than 1, a very large sample, let's say, of random numbers, this is where the random number generator comes in, from the distribution p, then I know by I think it's the law of large numbers, that this estimate of the mean will converge to what the true value is. In the limit, as you've got an infinite number of particles, this estimate will converge, and this estimate is just 1 over n, where n is the number of points, number of samples that you drew, and as n gets bigger, this gets closer and closer to the value that we're interested in. From the big picture standpoint, what this means is if you've got enough clock cycles where you can draw enough samples, you can get this mean as close to mu as you want. This is where Intel helps us, or we help Intel. I'm not sure which way it goes. There's a notational aspect of this that I don't like, but I'm going to use because it's in the papers and the book. And if I vary from their notation, I think it'll be more difficult to understand. The superscript I here means the sample. I made that a superscript because as soon as we start talking about state space models, the subscript is going to indicate the time of our estimate and what it's conditioned on. And so this was already taken, and the convention is to use I. Sometimes that I is in parentheses, but the convention in the particle filtering world is to use this superscript I. That is not a power. It's not x to the power of I. It's just the ith sample out of however many samples you have. So, and I'll be using that consistently. I almost changed it today, but I thought, no, it'll be too confusing, and my notation is different, so I used the same.
So x represents the state of the whole system, not of a particle. Is that correct? So x sub I, the I isn't referencing the particle. It's
yes, and a particle and a sample are the same.
Oh, they are.
Yes. So if one is an example, well, actually I'll give an example in a minute, but if I drew 500 samples from a random number generator that are independent of one another. And the third was a value of 2, the third sample, then that means x to the power, or x and then superscript 3, I may have transposed these in my mind, is equal to 2. This is just being an index of the sample. And with particles, we're going to have, eventually in the state space model, we'll have an entire trajectory that we're looking at, and each trajectory will be independent. So after the set of slides, when we start talking about time and state space models again, this will generalize and become a trajectory through the state space.
Okay, but is the trajectory of all the particles at once moving through the state, moving in time, or is it one particle moving?
When we talk about x to the I, superscript I, this is the ith particle only.
Okay.
And in this set of slides, it's a number, or possibly a vector. This could be, there's nothing to prevent in all this x from being a vector rather than a scalar. But next week, if it's a vector or scalar, it will also have a time history. And so it'll be that much bigger.
I see.
One key thing that's important to make this work, in order for this to converge, to use a statistical term, to the true value that we're trying to estimate, it's critical that these samples are drawn independently of one another. They've got to be statistically independent. And technically, a random number generator does not generate statistically independent samples, but everyone sort of ignores that, waves their hands, and says they're independent enough. I mean, it's seeded with one thing, and there's the state that a random number generator goes through, so it's actually a completely predictable sequence. Certainly not statistically independent, but it's designed to model that, and we ignore that, and we say it's good enough. We're engineers.
And it's what's replacement?
With
I mean, with the number generators that we build, that wouldn't normally come up, but
right.
theoretically it's with replacement.
I suppose theoretically it would be with replacement, yeah. You could get the same number again. A common choice for P of x, it's our decision. When we do this factoring, we get to choose what density we're using. And a common choice is to use a uniform distribution. It's not the best choice. We'll talk a lot about what the best choice is, but it's a choice that you can make. You can choose P of x to be anything you want, so long as the integral that you're evaluating, so long as it's non-zero of that whole range. You've got to make sure that your product of f of x times p of x is equal to g of x. And if p of x is 0 at some points, where g of x is not, then they're not equal, and you've wrecked it. So you've got to make sure that when you choose p of x, that it has the same support as g of x. But a common choice, the simple choice, the easiest thing to do, in some respects, is just to say, I'm going to choose it to be uniform. And we'll talk about why you wouldn't want to make that obvious simple choice later. But at least mathematically that works. And if you choose that, then you can make that choice. This is a little bit of theory that I'm not proving, but there's an important point. There's an important point buried in this. This is the integral that we're trying to evaluate. We're trying to get mu, where mu is we've expressed as an integral of the product of two functions, one of which is a PDF. And one of the things that we can think about is how far away is mu from g of x? And a common way of characterizing that is with mean squared error, or thinking about the variance of the difference. Those are more or less equivalent ideas. And so this is sort of a measure of goodness of fit. How close is, I have written g of x. I did something wrong. I'm sorry, I expressed this wrong. This is, if we do, this is a constant, and I explained this incorrectly. The variance is how far g of x is from it's the mu, the value of this integral on average. So we're integrating g of x, and this is how far away it is. And now I'm thinking, I need to go back and check my notes, because I'm not certain that's g of x and not f of x. But it doesn't matter, because this is some constant that is a property of the function that we're integrating. And the point that I actually wanted to make is down here, and that I was pointing to the wrong equation. The point I wanted to make is that in the limits, as n gets really big, it doesn't actually have to be infinity, but as it gets really big, the distribution of our estimate minus the thing we're trying to estimate, multiplied by the square root of n, the number of samples that we've generated, has a normal distribution with a constant variance. And why that's important is that is this bottom point here at the bottom of the slide. This is the point of the whole slide. The error, this is our error. The error of this estimate, it's constant if I multiply it by square root of n. So that basically means that the error of our estimate, or you can think of this as the standard deviation of our estimate versus the true, that difference, scales is the inverse of the square root of n. As n gets bigger, as we get more and more samples, our estimate gets more and more accurate. And really the main point isn't even written here. The most important point in this
That could be multidimensional, and then the minus the real mu, that's a Euclidean distance, right? Is that why? It doesn't matter how many dimensions we're looking at the distance from the real, or estimate from the real. That, in your equation where that in the limit as n approaches at infinity, just for n times. Is that really a Euclidean distance, because mu could be multidimensional?
Yeah, this notation is a little bit rough. Mu is a constant. I should have put this in a bold font, because mu hat is a random variable. And what this is saying is that the distribution of the difference multiplied by the square root of n has a normal distribution in this limit. There's a central limit theorem thing that kicks in, the distribution becomes normal, and the variance is constant. And so it's not really about a Euclidean distance. We're not doing a simple calculation, but rather we're talking about a random variable and what its distribution is here. Proving, but I'm just telling you that the math works out this way, is right here. The most important thing in this, and the reason that we're using this approach and not doing things numerically, is that this result, the fact that the error variance converge, I'm talking about the covariance in this case instead of the standard deviation. So the variance converges inversely proportional to the number of samples that you're using. That result does not depend on the dimension of the integral that we're evaluating. It converges just as quickly in 5,000 dimensions as it does in 1. And that wasn't true when we were talking about the Monte Carlo integration, where we didn't even hardly want to think about 2 dimensions, much less 5,000. This result here, the convergence, is just as fast, regardless of what the dimension is of the integral that you're evaluating. And so it looks, at first glance, that we just beat the curse of dimensionality. That this problem, the accuracy does not scale badly as we go to higher and higher dimensions. And there's a lot more discussion to be had about that we'll go through. But at first blush, this is the motivation for using this approach with state space methods.
I'm sorry, can we go back one slide? Is that because...
Make the main point again. It looks like we beat the curse, which is, huge. And in some respects true, and is the motivation for using this with state space methods. We've got very high dimensional integrals that you need to evaluate numerically. So now we've got to think a little bit more about this. Let me give you an example. Let's say we're given a random process where y is equal to the cosine of v. So this is a nonlinear function that relates the random variable y to cosine of v, and v has some normal distribution, 0 sigma squared v, so it's 0 mean and some variance that is given, and we wish to estimate the expected value of y. And this is a more specific case, because in this case, our integral that we're trying to evaluate, it's still just an integral, but it's already factored for us conveniently into some function and some PDF P of v. And so it just so happens in this case that the integral already is in the form that we like. And we want to evaluate that using. This begins to give you an idea of what the true and estimate looks like. This is simple enough that it can be evaluated analytically. We can actually calculate mathematically what the expected value of y is in this case. It's not a difficult integral to evaluate. It's an exercise we could do on the board. And that value in this example works out to be, I don't know what that number is, but it's shown by the horizontal red line. I somehow would almost wager it's 1 over the square root of 2, because it looks like that, but I don't know if it is or not. The estimates is I generated random numbers from a Gaussian distribution and then took the average, are shown by the blue line. And you can see it starts off kind of way off with the initial estimate and then rapidly sort of comes up to where the true value is and wanders around and then sort of gets down and then it takes a while and it comes back up. Then it wanders down again and then it comes back up. As you add more and more samples, the variance is getting smaller and it is getting closer and closer to the red line on average. But you can also see that, you know, most of your gains were made in the first, well, this is a large number, but the first 10, 20, 30 or so samples, that really got you in the region. And then there was sort of this point of diminishing returns, which is actually what you would expect. The standard deviation is 1 over the square root of n. The standard deviation of the blue, say, relative to the red. If I did a cloud of these, if I repeated this experiment 1,000 times, we would see it would start off all over the place, and then it would funnel down kind of like this. And then the rate at which it got closer would diminish as we got out more and more, because we've got 1 over square root of n convergence to what the true value is. So it gives you an idea of what's happening here. And although it's nice to say Intel solved all of our problems, you know, if we just make n big enough, we can get as close as we want. Well, that's true. If you want to be really close, it could be that you need a very large n. You know, even whether it's a scalar or multidimensional case. So that's the first sort of, yeah, theoretically n goes to infinity, but infinity is a long ways out. Yeah.
That's kind of, it seems like it could be problematic.
Yeah.
There's an oscillation to it.
It can be. It's just, I think, I was glad. I mean, I didn't do this deliberately, but I was actually glad to see that it came up and hit it and then it wandered down again, because there's nothing to stop it from doing that in one example. That's perfectly fine. That's to be expected. There is a variance, a variability about the true value, and as you add more samples, it's true that you get samples that push you in the wrong direction and your estimate may be off. You'll still win in the end, but you know, even if you're playing poker and with fixed cards and the odds are in your favor, you can still lose hands, and it's a similar idea here.
If you did, so would the blue be a trajectory of this? Would you consider that a trajectory? Or,
No, no, because this is as we add more and more samples, what our estimate is, and the trajectory is going to be one sample that evolves in time.
Okay, I was just wondering if you could do that for a bunch of them, you could take on average a bunch of those blue lines, and then maybe get a better estimate of the ensemble of those.
And you could, but if you're going to generate, let's say, 4,000 instead of 2,000, that would be equivalent to taking this out to 4,000.
So I wonder which it would be better estimate.
They're the same.
Yeah.
Yeah. And they're the same because all we're doing is taking our samples, putting them through the nonlinear function, and calculating an average. And this is just plotting what that average estimate is a function of how many terms were in that average. And so if I did this plot and said, okay, this is what the estimate looks like as you go out to 2,000, and then did it again, doing it again is equivalent to just adding more terms to the original sum. So
it's waffle.
this is the integral we want to evaluate. Optimal Bayesian recursions. This is what you're going to be implementing numerically in one dimension, and good luck if you're going to try to do it in more than one. You can, but you'll be waiting a long time. This is already in the form that we want. We've already got one function times a PDF and an integral that's already it's already factored for us. So it seems like, great. All we got to do then is draw samples from this distribution and then calculate the sample average of this function for those samples, and we're done. But it turns out it's not quite so easy. And the big problem that you run into, and it took me a long time to understand this. I mean, so far what we've talked about, when I first learned this, it was more or less intuitive. But the thing that tripped me up is this step, which is, okay, great, I've got an integral. You just taught me about Monte Carlo integration. Do it. Do it with this. We're done. We've got the PDF. And then you go and you sit down and you get ready to implement it, and you're like, okay, my PDF is this, and I've got to draw samples from it. And then you go and you look, okay, I've got rand in, I've got rand, I've got a small set of random number generators that can generate random variables from very well-known popular distributions. This is not that. This could be a gnarly, multimodal, ugly thing that you don't even have parameterized. It's not like a Gaussian distribution where I say, okay, it's Gaussian with a mean and a covariance, or even it's a Gaussian and it's got a mean and covariance, but I don't know what it is. In this case, we've got a multimodal thing, and it's not any of those. You don't have a finite set of parameters that characterizes this thing. So even thinking about how do we handle this, given that it's this big complicated thing with arbitrary complexity, even thinking about how to represent that is difficult, much less thinking about how are we going to draw samples from that. We don't have a way of drawing samples from that. You can't go to MATLAB and say, give me random numbers that comes from this complicated thing that I can't even describe to you. You can't do that. Or at least I don't know how to do that. And a lot of people have thought about this and come up with clever ways of approximately drawing things from this, but they're all approximations, and we'll be talking about them at length. And the bottom line is that you can't do what you really want to do, which is draw samples from this. You just can't. And so, it seems like, bam, we just hit a brick wall. We can't. Now what do we do? Where one of the tricks comes in. One of the tricks of Monte Carlo integration. In order for this to work, we've got to be able to run a random number generator, and however we factor g of x into a product of these two functions, the p of x, another constraint, in addition to being a PDF that is non-negative, has unit area, it's also got to be something that we can draw samples from. It can't really be arbitrary. It's something that's got to be practically useful, which means that we can go to MATLAB and draw samples from that distribution. And in our context, we can't. We can't even really describe the thing fully that we want to draw samples from. So, what do we do? One of the things that we can do, it'll turn out, is that for any value of x, we can evaluate it. We can evaluate this numerically pointwise. For a given value of x, we can figure out this is what we think the PDF is. But we can't draw samples from it. We can evaluate it numerically. If you say, what's the PDX when x is equal to 3.2, we can tell you that. But if you say, draw random samples from it, I'm sorry, we don't have a way of doing that. So one of the things that we can do is we can say, well, what I can do is instead of using p of x, let me draw samples from something that is available in MATLAB or Mathematica or whatever you're using, from another PDF that I'm going to call q of x. And this q of x is called the importance density for reasons I'll explain shortly. And there are a lot of random number generators. So you say, I'm not going to limit myself to p of x, but I'm going to choose an arbitrary q of x and draw random numbers from that. That's something you can do. That's practical. And so if, as in our case, g of x has already been factored, and this is the integral we want to evaluate, what we do is instead of drawing samples from p of x, we draw samples from a q of x. And we take this that's already been factored, and we factor it a little bit differently. We multiply and divide by q of x. clearly the same integral, q of x here, q of x in the denominator. And now what we're evaluating the integral of is this thing, but this is something that we can evaluate because we're drawing samples from q of x. And so we can do this approximation. But now when we calculate our sample average, rather than just having f of xi, we've got f of xi times the ratio of p of xi divided by q of xi. So if we're choosing a uniform distribution for q, then we've got a mathematical expression for that same q down here, and this is how we calculate mu hat of n. So we draw our samples, evaluate f, evaluate this ratio, take the sample average, and we get our estimate. This ratio of p over q, I'm going to denote as w. We're going to think of this as a weight, and w, and there's a tilde on it. We'll later, when we normalize the weights, we'll drop the tilde, but there's a tilde for now to indicate that these weights are not normalized. And it's defined, these non-normalized weights are defined as a ratio of the PDF that we wanted to draw samples from but couldn't, divided by the PDF of the samples that we actually drew the samples from. And as before, in order for this to work, q of x has got to have the same support, or I should say support everywhere that p of x has support. So wherever p of x is non-zero, q of x has got to be non-zero, or else you get a divide by zero mathematically, or you could say that your approximation is not going to work out because this isn't equal to that unless q of x is non-zero everywhere that p of x is non-zero. Any questions so far? Any questions on what we're doing?
Would you want to match the zero to the probability distribution?
It's not important. All you're doing, if q has more support than p of x, so you're drawing samples in a region where p of x is equal to 0, when you calculate the weight will be 0 in that case, and so you've wasted clock cycles, but that's all you've wasted. So it's inefficient computationally, but that's all you lose in having support in q of x where you don't have support in p of x. That's a good question. Anything else so far? You guys tracking this, so to speak? That's right. So q in this case is uniform, p is a normal distribution, and q has, I said it's got to have the same support. It can't technically have the same support, but I just made it really wide. So a really wide normal distribution. And what that means, I guess intuitively, a good way of thinking about this is because this is a uniform distribution, we're drawing a lot of samples in a region where it's improbable that if this is what we're evaluating, it's improbable that values would actually land there. And so a lot of these weights are small, and they're not significantly contributing to the mean. And so if we say you've got 800 of them, but some of them have a small weight associated with them, they're not helping you much. They're not contributing much in terms of helping you figure out what the mean really is. And intuitively, that's maybe a good way of understanding what went wrong. So mathematically, it looks like, oh, everything worked out, but it converges slower. And you don't see that in this math, but it's because when these weights are not equal, you get slower convergence of the thing we're trying to estimate to the true value. And we see that graphically in that example.
How did you come up with the weights, though? I thought that you did without the parameters for P. Wasn't that the problem? You couldn't draw from P to begin with, so how do you know what the ratio of P to Q is?
Good question. So there's an important difference here. It took me a while to recognize this as well. The situation that we're in is that for any value of x, we can evaluate what that PDF is. So for the normal distribution, you give me a value of x, I can tell you what the PDF is. What I can't do is draw random numbers from that distribution. I don't have I've got in MATLAB ease, the equivalent would be, I know what norm PDF is, but I don't have rand in.
If you knew it for all x, you would, right? You'd have the distribution.
We know it for all x, but knowing what the PDF is and being able to, or at least, and when I say knowing what it is,
I see what you're saying.
so as an instructor, it's so good to hear students make that expression, that noise. Although we can evaluate this function point-wise.
Right.
So when we say we know what it is, it's not as though, oh, it's a normal distribution. No. I've got this black box that if you give me an x, I can calculate it. But what I don't have is a random number generator that will draw random samples from that distribution. That's what I'm missing. But I can evaluate it. And so when I say, well, okay, I don't have that, I'm going to use a uniform distribution. I know I can evaluate this point-wise, and I've got a random number generator that will generate samples from it. I've got both with Q. I've only got one of them for P. And then I get down to here, so I drew a number, 3.2. I can put 3.2 in here and calculate that ratio and get the weight.
You know, what would be an interesting exercise would be to look at a uniform, drawing numbers out of a uniform distribution and just mathematically showing how you could create a Gaussian number generator from that with MATLAB. Do you have?
You can do that. There are ways of taking a random number generator that generates random numbers from one distribution and sort of shaping them so it's to another distribution. But that's hard to do in multi-dimensions. And I don't remember exactly where the problem is, but it doesn't get us out of this pickle. I wish it were that easy, but it's not. Right, so another example, same as what we did before. We want to evaluate the expected value of this cosine, where we know that in this case the PDF that we have, our P of V, is normally distributed. But let's just say for the moment, to make an analogous situation to what we'll encounter with state space methods, that we've only got a uniform random number generator. We don't have a Gaussian random number generator. What?
Obviously,
Here. So this is doing the same thing as before, except this time it's using that other approach where you're taking a weighted average with those unnormalized weight, and it looks the same as the previous example, but if you think back carefully, you remember that other one pretty rapidly converged to the mean. And you'll see this one does it more slowly. This one doesn't get there quite as quick. I mean, you can just see visually it comes up and a lot of kind of overshoot and a lot of variation here, and it varies more from what the mean is, after having 800 samples than it did before. I probably should have done an ensemble and done many examples so we could see a cloud of estimates and see how the variance doesn't decrease as rapidly in this case. So,
is that just your choice of weights? Is that what's the reason? Or?
Yeah, the difference is the story gets a little bit more complicated, but only a little bit. I mentioned those weights are unnormalized, which is only sort of true, but let me explain what I mean. If we look at these optimal Bayesian recursions, one of the things I sort of kicked under the rug consistently and didn't want you to ask a lot of questions about is, James, you keep saying that this doesn't matter, but yet it's still there in the equation. Surely it matters. Why do you keep ignoring that term? That term's troubling. I don't have that term. I don't know what it is. You tell me it's unimportant, but yet it's still there. And so it seems like we ought to deal with that. And that hopefully rubbed some of you the wrong way. It would me to just say, oh, don't worry about that. We'll deal with that later. Now's when we deal with it. We usually can't calculate this. It requires an integral, and in some respects, and this is where things get a little bit wishy-washy, I say it doesn't depend on x of n. Now, how much we care about this term depends on what we're going to do with the posterior. If we're trying to find the maximum, if we're doing what's called a map estimation, and we just want to pick the most probable value of x of n, then the maximum of this function on the right is not affected by this, because this only depends on y. Y is something we measure. It's a constant from the standpoint of evaluating this for a given set of measurements. So if we're doing map estimation, you should say, okay, in that case, I could see how that doesn't matter. But what if we decide that we want to do the mean of the posterior and use that as our estimate of x? If we want to do the mean, then surely this does matter. This is not a PDF on the right if we get rid of that term. It doesn't have unit area unless we include that term. That constant is important in order to satisfy this being a PDF and truly having unit area. If we take it away, it doesn't have it. And so the way that I think about what that term is doing is it's normalizing the posterior so that it has this property of a PDF. It's essential if we're going to calculate the mean. Otherwise, it'll be biased and it will be wrong. So how do we deal with that sort of in a good way where when it matters, it does, and yet we don't have to worry about evaluating another integral? And to make matters worse, the p of x that we've been talking about is something that I said we could evaluate it at any value of x. It's going to turn out that what we can evaluate is something that's proportional to p of x, but isn't truly p of x. So in the previous example where we had normal and uniform, so I can give you the normal PDF, but it's scaled by some unknown constant. And I can't tell you what that constant is because I don't want to calculate it. Nobody wants to calculate it. So we've got two places where bias can creep in, and it all comes from the fact that there's an unknown constant that we need to deal with. And if we look at the estimate, if we don't correct for this, again, if we do an expected value, if what we integrate or approximate the integral of is f of x times this p tilde, where p tilde is scaled by some constant that was just too much trouble for us to figure out, then if we go through and we do the math, what we end up with is that constant times our estimate of the mean that's unbiased. And if that constant is anything other than 1, it's going to bias the mean away from where it should be. It could amplify it, it could attenuate it, but at the end of the day, it's going to be biased, and we can do better than that. So we use a trick, and it's a clever trick. I like this one. It's not just sort of a sleight of hand. It's a reasonable thing to do. We can figure out the bias by taking the expected value of the function 1, using the same math, the same approach. We know that the expected value of 1 should be 1 if we've got a proper PDF. And so if we say, okay, what's the mean of 1 using p tilde? And we go through the same math. In this case, we're taking a sample average of the ratio of this p tilde, this scaled PDF, where we don't know what it's scaled by, divided by our cube, but multiplied by 1, because we're just taking this sample, this expected value of 1, and we end up with c times 1 over n times this sum of p of x of I over x of I. And what we know is that that ought to be equal to, if we've done things appropriately, this sample average of t of x of I over q of x of I should be equal to 1. And so this should be equal to c if it was scaled appropriately. And the cool thing about that is that means c is equal to this sum, which we can calculate. I know it's late in the lecture. We have to go over this again to get it. But the bottom line is the fact that we're off by a normalizing constant. We've got that p of I. We can figure out what it is. And after you've gone through and done this math and done this trick, you end up figuring out that it's just the sum of the average, I should say, the average of your weights that you were using. That's the normalizing constant. And so it's going to turn out that integral with y, that term with y, we don't care about because our estimate is going to be the same thing we had before with these unnormalized weights divided by a normalizing term, divided by the sum of the weights, the average of the weights. If you divide by the average of the weights, then you still end up with an unbiased estimate. And victory, you don't need that constant. You don't have to do another integral. You've saved a lot of computation. A way this is often expressed is rather than taking the ratio this way, is to calculate this sum and move it inside and normalize all of the weights individually by that term instead. And mathematically, that's a little more convenient. So all of you being at this level of your education shouldn't have any trouble seeing that this is equal to that. In this term, we take the unnormalized weights and divide by the sum of the weights is what we're going to call the normalized weights. And I'll denote that as just W of xi without a tilde on top to indicate that that's the weights. In which case, rather than taking the sample average, now we're just taking a weighted sum of f of x, where these weights are normalized in such a way that it's the right way and accounts for that issue of normalizing the PDF. You guys okay with this? Or maybe after studying it a couple of times, we'll be? Get there. I know it's late in the lecture. Maybe if we have time Monday. This is an even more abstract concept, and I don't know if we should wait, call it good for today, or if you guys want to see it. We've still got time left in the lecture, but if you guys are spent, there's not a lot of reason. Shall we go over it the first time now and maybe again on Monday?
Yeah.
Let's do it that way.
Rehash.
Okay, we'll do it that way. I understand retention levels may be low right now. We're going to be doing something crazy and something that we really have no business doing because our mathematical backgrounds are not deep enough. We're going to be using our friend, the impulse function, that you learned about as undergrads from an engineering perspective that makes mathematicians cringe. Mathematicians do not like functions that have infinitesimal supports and are infinitely high. There's a whole body of mathematics measure theory, I think, that is used to handle situations like this, where they go about it in a different, much more rigorous way than what we normally do. We're perfectly fine saying, oh, delta of x, it's infinitely high, it's infinitesimally wide, and it has unit area. And it's a problem with that.
It's a distribution, actually.
You can think of it as a distribution.
Mathematically, that's what's considered.
Your math background's probably deeper than mine, and at least in this territory, so you probably have a better sense of that. That may be true. I don't know that, but I know that we use this, and when I get together with my friends who are math professors, we have long discussions about this, and they roll their eyes when I show them some of the math that we use in engineering, which works perfectly well. As engineers, we can build stuff with this, but they express to me that you guys don't really know what you're doing here, and you're lucky you're getting away with this. This math doesn't really work the way you think it does, but nonetheless, we're going to roll with it, and we're going to turn up the volume by, rather than thinking about this in one dimension, we're going to think about a multi-dimensional impulse function. And we're going to go into thousands of dimensions with this thing. And it turns out the multivariate version of this can be treated as a product of the unidimensional versions. So if in 2 dimensions you've got an impulse of x, an impulse of y centered at some value, you multiply the two and you end up with the multivariate version of the impulse function. We don't normally think about that in undergraduate. We're usually only working with a scalar single-dimensional version, but in this class we need the multi-dimensional version, or at least that's how we're going to go. And now I'm going to attempt to express the same thing that we just went through from a different perspective using these impulse functions. And the key idea here, and this is where it gets really strange and weird, is that instead of thinking about estimating the mean, which is a perfectly proper thing to do, and the mathematicians don't mind if we say we're approximating integrals as sums, fine, there's no problem there. Where they cringe is when we start doing the math by saying, well, and what that really means, and we back that out, is that we are approximating the PDF as a sum of impulses, a sum of these multidimensional impulses, just to throw salt into the wound. So we've got a sum of impulses that are scattered about randomly. And the way that we do our math, we say, well, we really like these impulse functions, because if we take an impulse function, we've got these points scattered about, and this is now really a sum of impulses. This is an expression here. I've substituted in p of x. This is an estimate of the p of x we're interested in. But now we've got a p hat of x. And that p hat of x is really the sum of impulses. And again, the mathematicians are not liking this. But what we like about this is we can change the order of operations, the way we do math, and we can move this integration, shift it to the right, and instead of writing this as the integral of a sum, so these are linear operations, forget about infinity being involved for now, and we will instead say that we can express this as a sum of integrals. And now, when we integrate an impulse that is centered at x of I, all of you hopefully remember from your signals and systems course that that's just equal to f evaluated at x of I. And so the way that this is explained in the engineering literature is rather than saying we are approximating mu as a sum of f evaluated at specific points, instead we say no, we are approximating p of x with something that is very different than p of x, is the sum of impulses. And it's crazy to do that because in very few ways can you say that p hat of x is anything like p of x. This is usually smooth, it's well behaved, it's bounded. We're replacing it with something that has support almost nowhere except at a handful of points. And at those points it reaches up to infinity. And that's, in what way is that like p of x? But it is.
Just a sampled, if you mathematically sample that function or that distribution p of x, that's what you get.
It is, it's true. I mean, f of xi is what you get when you sample it randomly, but the idea of
Well, I'm saying
looking at it
when
inside.
you do sampling mathematically, they use the delta function in that way.
Okay, well, and
I mean, that's how we did it last term in engineering, but that's how it was written in the book.
I mean, that's kind of hand wavy, I think, because I mean, you're saying that like if you think of it with like array sampling, if you have an array of sensors and you're saying, these are delta functions, you're basically saying that they're going to catch things in the neighborhood of that delta function, even though they have infinitesimal support. You're basically, I don't know, it's kind of hard to explain, but you're trying to approximate something that is kind of a wide net with just these little points that seems like kind of a hand wavy argument. I don't know.
it's an approximation, but
Yeah.
But the good news is, as your net becomes infinitely fine, it converges to the right thing, as you would expect.
Yeah.
So
I mean, it works, but
I mean,
it's how the methods
that's just
work.
what we're doing with the integration, where, when we're doing it's the same deal, we're just doing a sum instead of, right? I mean, we're picking points and
It is
adding
true.
up. I mean, it's the same.
Yeah, and there's a lot less trouble with the idea of approximating an integral as a sum than there is with approximating a density with the sum of impulses. That's the step that is iffy, but we're going to do it anyway. At the end, the result is the same, and the mathematicians, despite their admonishments, arrive at the same result that we will. So, but I think it's helpful conceptually to say, what is our p hat? How are we approximating it? And it turns out that we're going to approximate it as a weighted sum of impulses. And when we use this approach, we arrive at exactly the same result. We did this once before, based on arguments that didn't need the impulse function, and now we are. And again, I want to raise in your mind the question of, in what sense can we really say that p hat is anything like p of x? They're not equal anywhere. And really the answer at the end of the day is that, well, they're similar in the sense that mu hat becomes like mu when you get enough of those. It's that the integrals are equal, not that but nonetheless, it's useful, I think, to have this kind of picture in mind. This is an example where a normal distribution is represented as impulses that were drawn from a normal distribution. No, I'm sorry, these impulses were drawn from I said it right, from a normal distribution. So the impulses are drawn from the same distribution shown by the blue line, and what we're going to be doing in this class, the way particle filters work, is instead of using the blue line, representing the blue line, We say we've got this swarm, we've got this set of particles that's represented by all the points here. And in this case, we say it's a valid representation. If you were to do a histogram of where the impulses were located, you would see that as you add more and more, it converges to what the blue line is. Small note on notation, I know impulses are normally represented as arrows, but I'm not going to have any other reason to put vertical lines on here, and all the arrowheads would overlap and cause aliasing in your mind, and I'm just going to use it as vertical lines. It's a little bit like a scatter plot.
There's no weighting on those right now, right?
There isn't yet. That's right. So this is impulses that were drawn from a normal distribution, and I just plotted a vertical line where those impulses fell, and I wanted you to think, okay, those impulses are how we are going to represent the PDF shown in blue. And it's weird. The impulses are not the PDF. It's just a finite set of points. And yet that's what we're going to be doing our computation with. And it works in the sense that whether we do integrals with the blue or do integrals with impulses located where these vertical lines are, we get more or less the same result. Now, I think I've mostly made these points. One of the things that you gain from working with this swarm of points to represent our PDF is that we can not only, we're not limited to just calculating integrals, we can also look at percentiles. And that's extremely helpful when you're doing signal processing, to be able to say, I've got an estimate of the state is at, I'm estimating it to be at 7, but then to be able to say with 95% confidence it is greater than 5 and less than 11, that's really helpful. And with these impulses, we can do that. Representing the PDF that way, we say, well, give me where the 2.5% is and the 97.5th percentile is, and we can calculate that. It's less clear how you would find a mode. If you're trying to find the peak in this smooth, well-behaved PDF, but what you've got is all these impulses that reach up to infinity, and you say, well, where's the maximum of that function? That's a little more problematic. And we'll talk more about that later, but some things to think about. And then to expand a little on what Adam was talking about, with, in our case, we're actually going to have weighted impulses because we can't draw from the distribution that we want to. And so our p hat of x is going to be the sum of weighted impulses, where these are the same weights as before. You draw from one distribution, you're trying to model another distribution. This is the ratio of those distributions at the locations of the particles, the samples that you drew. And so we've got a weighted PDF, and just to show you an example, this is more representative of what we're going to be working with. In this case, I drew the random numbers from a student's t distribution with 2 degrees of freedom. And all you really need to know about that is that it is it's a flatter distribution with heavier tails than the Gaussian distribution. So the student t distribution is, if I did that backwards, it must actually be narrower, looking at the shape of this, because here the weights are attenuated, which means Q is higher than the blue. I should have plotted it on top of there. I'll update the slide so it's plotted on top. So here it's higher, and out here it's lower, and stays lower because these weights are greater. But I guess the main idea I want to get across is that we're going to have weighted impulses. And sometimes we'll have impulses out here where the PDF is small, and these are going to get weighted small. And that's bad. If you've got small weights, then it's not contributing significantly to your estimate of the mean. Ideally, you want the weights to be uniform. When they're not uniform, in some senses, you're wasting some clock cycles. You're wasting some of your samples. So that's the picture to keep in mind as you go into the weekend and relax because your homework isn't due on Monday, and then get ready for the lecture on Monday. So we'll pick it up and go over some of these main points on Monday. Have good weekends, guys.